Hey there, Calc folks. Back here with another lecture. This is one that I lost audio to. Somehow my recording software here, OBS, did not. Well, somehow the mic got switched off, disabled. I don't know. I know I had a Windows update last week sometime and lost some. Well, didn't lose anything then, but updated my system, and that could have been maybe the culprit. But I did record and post some videos that didn't have sound, and I got to come back and re-record those, folks. And that is what I am doing here today. I'm looking at planes tangent to the surfaces again, and presenting to you this material one more time here, folks. But that's fine. It is a quick lesson, and I can go back through it with you again here, folks. What we are looking at in this section, if I flip over to the notes, we are looking at planes tangent to surfaces. Right? That is our topic at hand. And I do say surfaces here, folks, because the way this initially develops is that it develops for any surface in n-dimensional space. That surface does not necessarily have to be functional in behavior. So when I set this up, I set it up initially for planes tangent to surfaces as opposed to planes tangent to multivariable functions, because the case for a multivariable function is really just a special case. Right? This technique actually works for any three-dimensional surface. All right? That is what we should take note here to begin with. Second of all, we are going to recall a little bit from our previous calc study of planes in three-dimensional space, and we're going to use our understanding of the plane in three-dimensional space to build the equation of the plane here that's going to be tangent to our surface. So to begin with, let's just recall, right, that a plane in three-dimensional space is defined, right, by a coordinate on that plane and a direction orthogonal to that plane. All right? To define any plane in three-dimensional space, remember, you're going to need a coordinate on that plane, and you're going to need a direction orthogonal to that plane. All right? With those two pieces of information, you can define a plane. All right? Recall that if we let x null, y null, z null be a point on the plane, and we let v bar equal to the vector abc be a vector orthogonal to the plane, right? Then, right, recall the plane in R3 is going to be defined by this equation seen here. It is going to be a times x minus x null plus b times y minus y null plus c times z minus z null, all set equal to 0. This produces the general form of the equation for a plane in three-dimensional space. All right? Passing through the point x null, y null, z null, right, in the direction of the vector a, b, c in value. All right? In the case for the plane tangent to the surface, though, the point of tangent behavior will actually end up being the point, right, on our tangent plane, right? The point of tangent behavior, the coordinate at that tangent behavior is going to be what describes x null, y null, z null. As for the direction orthogonal to this tangent plane, we're going to exploit a property of the gradient. That property stating that the gradient of a surface is orthogonal to a level curve passing through the location of this gradient in the domain of this surface. All right? We're going to exploit this property that the gradient is orthogonal to level curves. Right? The gradient of a surface is orthogonal to the level curve for the surface passing through the location of the gradient in the domain of the surface, or in the domain of the function. All right? We're going to exploit that here. right? We're going to think of all of our surfaces that we're looking for the tangent plane of as actually just being level curves for higher dimensional surfaces. We're going to think about all of our surfaces in 3 dimensions that we can calculate the tangent plane to as being a level curve for a 4-dimensional hypersurface. Right? With that 4-dimensional hypersurface, we can find the description of the gradient for it, which will exist in 3 dimensions. And at the coordinate of tangency, with the coordinate of tangent behavior, that gradient is going to be orthogonal to our surface, and thus orthogonal to our tangent plane. And we're going to use that gradient vector. All right. What we are going to be calculating here, folks, is the plane tangent to the surface. This is an illustration of that tangent plane, seen here. All right. This is our surface. And this blue plane, planar region, is the plane tangent to our surface. Right? To define that tangent plane, we're going to need a point on the surface, which is highlighted in red there. That is the point on our surface. And we're going to need a direction orthogonal to our surface, and that is this red vector that is extending from our surface. Right? This red vector is actually going to be the gradient for a higher dimensional surface whose level curve looks like this illustration seen here for this surface. All right. We're going to exploit that gradient property of that higher dimensional surface to find this direction of orthogonal behavior to both the surface and to our tangent plane. All right. I do have an illustration of this on Mathematica. Let me see if I can bring this up. Yeah. Let's see here. I got to close the one that's currently open. Let's not. We can skip over saving that. But it should open up to this one. Then if I scroll down, here is an illustration of that tangent plane that I have for you. Right? Where I actually can roll it around here in space. So you can actually see its tangent behavior. Right? The way I did calculate this plane is I'm going to define it using that point of tangent behavior, that point seen in red right here, right? And I'm going to define it using this direction of orthogonal behavior. Right? This red vector's direction seen here. That is our direction of orthogonal behavior. And the way I'm going to find that direction of orthogonal behavior is I'm going to treat my surface as a level curve for a higher dimensional surface. All right? Now, all of this is set up as followed. All right. If I scroll down here, I do note, to exploit this property for a surface S, S will be treated as a level curve for a higher dimensional surface. Big F bar, where big F bar is going to exist in 4 dimensions when our surface of interest exists in 3. The orthogonal vector for the tangent plane will be given by the gradient of this higher dimensional function. It'll be given by the gradient of big F bar, or big F at x, y, z. And it'll be at that location, x null, y null, z null in value. All right. Where this is formalized in the definition below. All right. Letting the level curve defined by this 4-dimensional function at big F at x, y, z equal to 0 represent a surface in 3 dimensions. The plane tangent to the surface at the coordinate x null, y null, z null is going to be given by this equation here. It is an equation that is built by taking the dot product, notice this is a dot product, between the gradient vector at x null, y null, z null, and this vector that forms in three-dimensional, in three-dimensional space defined by x minus x null, y minus y null, and z minus z null as its coordinates. The gradient vector at x null, y null, z null being a three-dimensional vector description made up of the partials of big F will lead to this formulation seen down below here. You will have the partial of big F with respect to x at x null, y null, z null times x minus x null, added to the partial of big F at x null, y null, z null times y minus y null, added to the partial of big F of z with respect to z at x null, y null, z null times z minus z null, all set equal to 0 here. All right. This will produce that equation of the tangent plane. Right? Orthogonal direction described by these three partials at x null, y null, z null, and passing through the coordinate x null, y null, z null on the surface. All right. Let's look at an example. Consider the surface described by the unit sphere x squared plus y squared plus z squared equals 1. A sphere centered at the origin in three-dimensional space with a radius of 1 unit is described by this equation here. And it's not functional in its behavior. Unit spheres are not multivariable functions. Their upper half, the upper hemisphere might be, and the lower hemisphere might be, but collectively the unit sphere is not. But what we have is a technique for finding tangent planes to surfaces, not functions here, folks. So we can work through this. What we're going to do is we're going to think about our unit sphere as being a level curve for a higher dimensional surface. And the way we're going to express that level curve is by setting this equal to 0 and defining our level or our hyperdimensional surface as the function that's set equal to 0. The expression that's set equal to 0. All right. If we, letting this equation represent the level curve defined here, setting it equal to 0, we can define our level curve big F set equal to 0, where big F is the statement x squared plus y squared plus z squared minus 1 in value. We're taking its partials and forming the gradient vector. You will form the three-dimensional vector 2x, 2y, 2z in value. Right? This is going to describe the direction orthogonal to any point on our unit sphere. Right? So, the plane tangent to the sphere at every coordinate x null, y null, z null on the sphere will be described by this equation here, where since our gradient vector is 2x, 2y, 2z at x null, y null, z null, it'll be 2x null, 2y null, 2z null in value. And the tangent plane will be the dot product of this three-dimensional vector with this three-dimensional vector. Or will produce this equation seen here. Right? Where what that equation does is describe any plane tangent to the unit sphere at some arbitrary coordinate x null, y null, z null. Plug in any arbitrary x null, y null, z null coordinate into that equation, and you'll have the equation of the plane tangent to that unit sphere at that coordinate. Right? For example, the coordinate 1/2, comma, root 2 over 2 is on the unit sphere. So plugging that value for x null, y null, z null into this equation for x null, y null, and z null, right? 1/2 for x null, 1/2 for y null, root 2 over 2 for z null, you build this equation seen here, which can be simplified. You can expand, right? Combine like terms and solve it for z, and you might end up expressing this equation seen here. Right? This would be our general form. This would be our functional description of that tangent plane. Right? Defined as a dependent relationship, z dependent upon variables x and y. Right? Tangent planes, folks. All we're doing here is using this equation of a plane, using the point of tangent behavior to describe the point on our plane, and using the property that a gradient is orthogonal to a level curve, and defining our surface as a higher dimensional level curve, right? Define that direction of tangential behavior, or that direction of orthogonal behavior, to substitute all that into our equation for the tangent plane. All right? Now, this was all a setup for any surface. There does exist a setup for functions. This is what we see developed down below here. In this case, folks, right, the case where our surface is defined functionally, right, S is defined by this surface in three-dimensional space where z equals f of x comma y is a functional relationship contained in 3 dimensions. The above definition of the plane tangent to z equal to f of x comma y at the coordinate x null y null z null, which would correspond to the coordinate x null y null f at x null y null, right, can then be described by this equation seen here, where f, little f's first partial with respect to x at x null y null times x minus x null added to little f's first partial with respect to y for x null y null multiplied by y minus y null minus the quantity z minus f at x null y null, all equal to 0. Right? Where again, little f's first partials with respect to x and y are being used here. And this is all because big F, right? Big F, the level curve, is being defined as little f of x comma y minus z in value. If you take z equal to f of x comma y and you solve it for 0, set it equal to 0 to define your level curve, you will define your level curve as f of x comma y minus z in value. So the partial of this with respect to x will only be the partial of little f with respect to x. And the partial of this with respect to y will only be the partial of little f with respect to y. And we see that here and here. Whereas the partial with respect to z will come from just the negative z, and that will just be -1 in value. So that term will turn negative in our calculation here, inside the equation. All right. It is our calculation given above, but because of the specifics of the surface, we see a very specific case for the level curve. And it defines itself as we see here. Now, let's look at an example. All right. Consider the plane tangent to the curve f of x comma y equal to x squared, y cubed at this coordinate x, y, z equal to -2 comma -1 comma -4 in value. In this case, we take the partial of this with respect to x, we get 2xy cubed. If we take the partial of little f with respect to y, we get 3x squared y squared, implying at the xy location of -2 comma -1, those first partials produce 4 and 12 respectively for x and y. Right? Those first partials, along with our coordinate, can be plugged into our formula to develop this equation of the tangent plane. where that does simplify into this, implying that if you solve that for z, you will have this statement seen here. Z would equal 4x plus 12y minus 16 in value. Equations of tangent planes, folks. We are using our knowledge of planes, right, to define these equations of the tangent planes. We are using that point of tangent behavior as the point on our tangent plane. And to find the direction orthogonal to the tangent plane, we are treating our surfaces as level curves for higher dimensional functions. We are taking our descriptions of our surfaces in three-dimensional space, setting them equal to 0, which defines them as a level curve for a higher dimensional function. That is what this definition is telling us to do initially. Define our surface as this level curve. Once defined as a level curve, you can then just use the gradient of that higher dimensional surface dotted with this vector of components x minus x null, y minus y null, z minus z null to form your equation of the tangent plane. Dotting that and setting it equal to 0 will form the equation of the tangent plane. All right. And then there is the special case of a functional surface. That is kind of a unique case. And in that case, your level curve is defined this way, which does simplify how your equation is defined. All right. But that is tangent planes, folks. There's not much more to this. I'll work through a couple more examples in class. But again, here, what we're making use of is partials, folks. Partial derivatives. Partials with respect to x and y. For the case of defining the plane tangent to a surface that is functional, or using the partials of big F of x, y, and z, right, in the case that we're just dealing with any old surface. But it is an application of partials. And more so, it is also an application of gradient. Right? We are using the gradient of this higher dimensional surface to define our direction of tangent, our direction of orthogonal behavior. All right. With that said, I hope you're hanging in there. We don't have much left to this chapter. I do want to look at some extreme values, look at extreme values on open intervals, local extreme values, and looking at absolute extreme values on closed intervals. I got 2 more lecture videos to present over those 2 topics, folks. And I'll have those out for you shortly. All right. I'll see you in class.